Welcome to the STEM Pathways podcast, where we delve into the fascinating world of science, technology, engineering, and math. I'm your host, Rohan Sharma, a passionate explorer of all things STEM. Each episode, we bring you captivating stories, cutting edge research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student, a professional, or just curious about how the world works, join us as we unlock the mysteries of the universe and explore the endless possibilities of STEM. Let's get started. Today, I'll be interviewing Dan Mancheski, who's currently working on his undergraduate degree in nuclear engineering at UW Madison. How are you doing today?
Good. How about yourself? How are you doing?
Yeah, I'm doing good as well. So to start off with, what made you decide on your major?
Sure. That happened. When I applied to Madison, I applied directly into the nuclear engineering program. I knew that I wanted to do nuke back in high school. I first was introduced to it actually through Boy Scouts. The University of Madison provides a nuclear science merit badge that we put on twice a semester, and now I'm a part of that. But as a Boy Scout in high school, I went through that program and I got my nuclear science merit badge, which was really fun. I enjoyed it a lot, and I loved the idea behind a clean energy source like nuclear. Um, in high school, I also really enjoyed STEM subjects, math, physics, and chemistry. And then eventually, when I transitioned into college, I learned that nuclear there isn't a whole lot of chemistry involved. It heavily focuses on math and physics, but at the time being, I didn't know that. So that's really what sparked my interest. I liked the classes in high school, as well as I took the nuclear science merit badge in
Yeah,
through the UW Madison program.
yeah. I'm also a Boy Scout.
Oh,
Uh,
awesome. Wonderful.
yeah,
Are you going
yeah.
to
I
be an
just got
Eagle
my
Scout?
Eagle. Yeah, I got it back in December.
Congratulations. Congratulations.
Yeah. So you lived in Madison?
I didn't. I lived actually up in Appleton, Wisconsin, about an hour and a half north of here.
Yeah,
And I went to one of the schools up there. And then my troop every couple of years would come down to Madison to participate in that merit badge.
yeah. No, I know I didn't do that one, but I have done some with UW Madison before. But yeah.
Sure. I mean, if you're interested, I'm now the contact person for it. So if your troop is ever interested, or anyone that's listening, if you're interested, feel free to reach out. We do offer this merit badge twice a semester. So
And then I guess next I kind of want to ask you what your experience has been like while majoring in it.
sure, yeah. So my experience, I started out in 2020, really when COVID started to hit. So all online classes, everything like that. The campus was pretty much on lockdown, so a shaky start. Um, I'm not a huge fan of online classes. I'd much rather prefer the in-person learning. I feel that it's just a better way to connect with your professor, get to know them, ask questions, and such along those lines. So I didn't really enjoy it a whole lot my first few years. However, as I sort of moved up and as we recovered from COVID, got back more into in-person classes, I took a class or a few classes my sophomore year. One of which being NE 234, which is an early on nuclear specific course. In this course, it's called I believe it's the Principles and Practices of Nuclear Engineering. It's where for 5 days a week, 1 hour a day, you would come into the classroom and you learn about the physics or basic physics behind nuclear reactors, how they operate. And then on top of that, you would come in for a 1 hour session every week where you could actually go in and get to operate the reactor under the supervision of a licensed reactor operator. That also helped to sort of spike my interest in nuclear. I loved that course. I loved operating the reactor. And then after that course concluded, I was given the opportunity to apply to become a nuclear reactor operator. Um, I then went on to do another independent study course where we did some more training. We did some more lectures on nuclear physics, or reactor physics rather, and then practiced for the NRC licensing exam. Um, and this maybe I'm going off on a tangent about how I became a reactor operator, but this was also sort of along with my college career in the courses that I took. Um, so early on, I was introduced into nuclear, and now actually I should say that we have a freshman course now that we offer for nuclear engineering prospects. It's a course where you get to come in and work as a team to design actually a Cherenkov detector, which is a radiation detector that we actually go and put in the nuclear reactor and get to test in the nuclear reactor towards the end of the semester, which is I've heard it's a lot of fun. I didn't take that course, but we do offer it now. So it's sort of let's first year nuclear engineers get a taste of what it's going to be like in future courses. But my career, then in your junior year, you really get into the hard hitting nuclear physics courses. You take courses on modern physics and quantum, and then getting into nuclear and nuclear reactor design a little bit. And so those are some of the hard hitting junior courses. And then moving into your senior year, you get into more of the, I guess, more nuclear courses. And as a senior design project, then you get to go ahead and either do a project for a company or just a for fun project where you get to design your own reactor as a group and hopefully make it function. So that's sort of the pathway for a nuclear engineer at Madison.
Yeah. How would you, is nuclear engineering probably one of the harder engineering majors, or?
Well, I don't know. I can't say. I haven't done any other engineering, but you know, it might be harder than civil engineering. We can say that. Sorry to all my civil engineers.
Yeah. So, can you talk a little bit about what a nuclear reactor looks like, first of all? I got to see it last week, which is really cool.
Sure, yeah, of course. So our nuclear reactor, it's actually quite small compared to a power plant. Our nuclear reactor, it's only about a 3-foot cube of fuel rods and control blades and such. A power plant is going to be a much larger structure. They're, I shouldn't say usually because there are all sorts of different designs, but much larger than what we have here, 20 feet tall, more than 3 feet by 3 feet in footprint. So they're much larger, but ours consists of a smaller amount of uranium, and ours is only about a 3-foot cube. We have control blades, which is how we control the reactor. Ours has 4 control blades along with a 5th control element, which is it's actually a cylindrical rod instead of a blade shape. And then we also have our fuel assemblies, which are 4 fuel pins arranged in a square fuel bundle, as well as graphite reflectors, which are sort of square aluminum elements with graphite on the inside to help reflect neutrons from escaping the core.
Yeah. And then all of that, of course, is in a 20-foot tall tank of water.
Yes,
Yeah.
yeah. So we have a big pool of water, and the water is used for a few different purposes. One, it serves as a coolant. So as the reactor turns on, it heats up, and that's how we provide energy in the form of thermal energy, which then we can convert to electrical energy in a very similar process as like other power plants, coal, natural gas, such like that. We just boil the water. So it serves as a coolant to the reactor fuel itself. It serves as a moderator, which is what allows fission neutrons to slow down. Neutrons born from fission reactions are actually moving too fast to cause another fission reaction, especially in our type of reactor. In a fast reactor, that's not the case. But in our type of reactor, in most power reactors, those neutrons are going to have to slow down before they can cause another fission event. So the water helps slow down those neutrons so that they can fission more fuel and produce more energy. And then the water also acts as a shield. So we're actually able to stand up at the top of our pool and look down through about 20 feet of water at the reactor core, even while it's operating, because all that radiation is getting shielded by that water.
Yeah. Can you talk about some potential career paths that you can take as a nuclear engineer?
Yeah, certainly. So career paths as a nuclear engineer, there's quite a few areas that you can get into. The obvious one, you can get into power reactor engineering. So you can go to a power reactor. There's a few different engineering areas that you can get into. Can get into general engineering, which is like on-site engineering at the reactor for day-to-day engineering duties. You can become like an operations engineer, where you go in during refuels and first startups, and you get to go and engineer the first startup of the new core. or you can become like a core engineer where you sit down at a desk and you run the programs to design the new cores for when fuel has to be rotated out. So those are a few of the positions there. You can go into regulation, the NRC, the IAEA. Those are two big regulation bodies, governing bodies that govern a lot of the reactors in the U.S. The NRC specifically, and then the IAEA is more of like an international body. You can go into policy in the U.S. government. You can go into research. That's another big one. Actually, about 30 or 40% of the undergraduates from Madison go into research, higher education, or research positions at a private company, or national labs. That's part of research as well. As well as medicine. Medicine's another big area. At Madison, we actually have two separate tracks. We have a track for power, and then we have a track for medicine or health physics. So the health physics track, you can either go into like radiography, imaging using radiation. You can go into cancer treatment type jobs, or you can go into like a health physics job where your concern is to monitor where radiation is and put the security, or not security, I shouldn't say security, the safety procedures in place to limit exposure to the public or to individuals.
Yeah. Do you need a master's or PhD for most of these?
You don't. Well, it helps. It helps to get a higher education degree beyond a bachelor's degree. For a lot of the engineering positions, you can actually go into a company as a bachelor graduate, and they'll put you through the entry level engineering positions in nuclear, and then a lot of times what they do is they'll actually pay for you to go back to school to get your master's or your PhD, just to become more like a understand the certain topics or certain specific topics a little bit above your peers. And so if they pay you to do that, then you can always go back and you can get a master's or PhD. A lot of times research, national labs or university research positions, they will ask for a higher degree, a master's or a PhD, but those you can always get while you're researching as well. So a lot of these positions, it doesn't require it, but it does help to go on and get a
Yeah.
master's or a PhD.
Is nuclear engineering one of the fields where a lot of people work for a bit after getting their undergrad and then get their degree later?
Yeah. So I don't know the exact number on this. I don't want to say a number that isn't true. But if we have about 30 to 40% of our undergrads going back to school to get their master's, whether it's at Madison or another university, then probably 60, 70% of the students go on to go get a job. And from the people that I've talked to and the people that I know that have graduated in the past, maybe another 30% of those go back to get their master's, at least in 1 or 2 years after they graduate. Further down the road than that, I'm not sure, but I do know it's a significant number of people that come back to get their master's at least.
Wait, so when I was there last week, I think you said something like 25 nuclear reactors in universities.
Yep.
Uh,
So there's 25 universities with reactors on their campus.
oh, is that in the world or the US?
That's just in the U.S. So in the world, I'm sure there's more. I don't know the figures for outside
Yeah.
the U.S. though.
Are there nuclear um programs for undergraduates in the universities without reactors, or is it mostly just in those 25?
Yeah, so there actually are quite a few universities that offer nuclear engineering without a reactor. A reactor is not required to have a nuclear engineering program. It is nice to actually be able to go up to a reactor and see all the things that you're learning in class on paper. One of our senior level courses here is reactor theory, but it's a lab. So it takes all the reactor theory that we've learned in previous courses, and then we go and operate the reactor, and we show that theory actually exists in real life by doing all those different operations.
Mhm. What career path do you see yourself headed on right now?
So right now, I'm looking to get into the power industry. I don't know where yet, whether it's operations or core design. I'm not quite sure. But as I'm getting into my senior year now, I'm gonna have to start taking a pretty good look at what I actually want to do, and then start applying to some of those companies.
Yeah. Wait, do you know how many reactors there are in the U.S.?
I don't. I want to say there's almost 100 operating cores, but there can be multiple cores at a single plant. Some plants have two, three, four cores. Um, but I know there's approximately 100 operating cores. I want to say maybe 96.
Okay. Uh, will you say they're fairly spread out, or are they mostly in certain locations?
Yeah, that's a great question. So there's areas in the U.S. that they're more highly concentrated in. Along the East Coast, there's quite a few reactors. The Southwest, there's a couple, and just the southeast area, there's a lot. In the West and the Midwest, there's not as many reactors. Why that is, I'm sure there's an economic reason. However, I'm not too familiar in that area. So yeah, they're concentrated along the east, southeast, and coastal
Yeah.
regions of the U.S.
How do you think like nuclear jobs are going to be changing over the next probably like 10, 20 years as we
That's
shift to
a
more and more nuclear energy?
yes. So that's a loaded question. Fission nuclear engineers. I hope that the job market increases. I know a lot of the younger adults now growing up into college and getting older. There's a lot of enthusiasm behind nuclear in that age group, and I think that's going to help uh, push nuclear energy as a clean energy source that's safe. Um, a lot of people have concerns about the safety of it, and in the past, the older generations they have reason to be concerned about it. They've experienced three major nuclear accidents, and they've seen all those in the news. Um, However, the security and the safety of reactors is ever increasing. There's so many regulations to operate a reactor that it's challenging to even get them built now. But I think as the enthusiasm of the younger generation starts coming in, we're going to see more reactors, hopefully, and so that would then produce more jobs for nuclear engineers. Um, as for the fusion side of things, there's always advancements in the fusion research. In the news, you always see something about fusion, new records being set. Uh, the saying goes, "It's only 10 years away," or "It's only 20 years away," and we've been saying that for the past 60 years. So, who knows? Fusion, it might reach a point where we can actually produce power from it and commercialize it, which would be very good, and that would offer a lot of jobs as well.
Yeah. How similar is do people who go into those fusion reactors would they basically do the same classes as you?
That's a great question. So you can take the nuclear engineering route and then get a position in the fusion industry. A lot of students I know, however, actually get a degree in engineering physics and then a focus in like plasma physics. Um, so that's where a lot of plasma physicists. I don't want to speak for all plasma physicists. I'm sure there's other positions out there, and I'm not too familiar with that. But I have a good friend that got an engineering physics degree from the University of Wisconsin-Platteville, and he might be going into the fusion industry. So, um,
Yeah.
yeah,
Yeah, I had to see the fusion reactor too last week, and it looked extremely complicated.
yeah. I know there was
But
just some breakthrough research done at the WAM group here at Madison. I couldn't tell you what it was. I didn't read the article, unfortunately.
yeah, but yeah, it definitely looked interesting. As from what they were saying, I guess they kind of said what you said about like it's going to be in 10, 20 years, and they've been saying that for a while. But if it does work, it looks like it has a lot of potential.
Yes, it certainly has a lot of potential. I'm all aboard the fusion train. If we get it working, awesome. But I know right now, currently, fission is reliable, so that's where I'm at for my career.
Yeah. Um, can you talk a little bit about what people are doing research in at these national labs or universities?
Sure. Right now, I know a lot of investment is in new materials and material research. I'm sure there's a tons of research projects going on. I wouldn't know where to even start with a lot of this research, but one that I am familiar with is material research. A lot of groups are looking for better materials to build fuel cladding out of, or to increase the both the safety of fuel cladding in like a loss of coolant accident. So in case all the water drains out of a power reactor, how to prevent that fuel cladding from melting or weakening to the point where it can burst under pressure and such like that. So there's a lot of research in the safety of fuel, and then there's a lot of research for materials for operating reactors at a higher temperature. Currently, reactor fuel cladding is made out of, it's a zirconium-based alloy. And zirconium has a high melting point. It can withstand our current fuels and our current operating temperatures. However, we could operate reactors at a higher temperature and have a better output of power from them, a more efficient output, if we could operate them at higher temperatures. In Madison, most engineers will go through a thermodynamics class where you learn that you can actually become much more efficient if you operate something at a higher temperature. Say if we have our coolant at like 1500 degrees Celsius instead of 1000 degrees Celsius, and then turn it into steam and then cool the steam down only about 100 degrees, or I don't want to give numbers for that, but operating at a higher temperature is more efficient for power generation. So if we're able to operate the reactor at a higher power or a higher temperature, we can get more efficient output from it. So there's research being done into that.
Oh, what's the zirconium thing exactly?
Yeah, so zirconium is it's a metal. It's what the fuel cladding is made out of. So in a fuel pin, you have the uranium, of course, and
And
then
the fuel pins are the metal rods that the uranium's inside of.
yes, yeah. So the fuel pin is the whole metal rod, the whole thing combined. The uranium is on the inside of that metal rod, and that metal rod, it's actually just a hollow metal tube, and the metal tube is actually very, very thin. It's called the cladding, and that's what the zirconium-based alloy is made out of. I know there's a couple of promising new claddings coming out of Framatome and Westinghouse called Axiom cladding, and I believe it's M5 cladding from Framatome, but those are going to be their primary research and primary claddings for their next generation reactors.
Yeah. And wait, so when the reactor is being used, is an entire reaction occurring within the rod?
Yeah,
And
so
then
it's a
those
good
rods
question.
are heating up?
Yep. So those fuel pins in our reactor specifically, we have 83 of them. In a power reactor, there's hundreds of them. And so the reaction is happening within those fuel pins inside the uranium itself. Each uranium atom is being split by a neutron and an incoming neutron. And then when it splits, it turns into two smaller atoms and shoots out some more neutrons. And then the smaller atoms, they actually carry most of the energy from the fission event. And then that energy is transferred to the water in the form of heat.
Oh, yeah. Wait, so the reaction occurs inside of it, it heats up the rods a ton. And then
Yep.
oh yeah. And
Yeah, so
then,
the uranium heats up, which then heats up the fuel cladding, and then heats up the water around the fuel cladding. And that water is pushed either through natural convection in our reactor or in a power reactor forced convection, and then that's gonna boil either that primary coolant or a secondary steam loop.
yeah.
But the end goal is to get steam.
Wait, you said there's how many pins in your reactor?
Ours has 83.
I thought I just saw like a few of those like rod things.
Yeah,
Oh,
so the fuel bundles are what was at the very bottom of the reactor core there. The ones running all the way to the top of the pool, those were the connecting rods for the control blades. So we have 4 control blades. Those were the rods running all the way from the core to the top of the pool. And then they had motors at the top of the pool. That's what would lift and lower the control blades.
okay. Yeah. So, can you talk about other research then that's also being done?
Sure. Other research. So I know there is a little bit of investment. Well, actually, I should start with this. So medical research, that's always a big one. Um, Radioactive isotopes for both like cancer imaging, binding radioactive particles to other proteins or sugars in the body to locate different things in the body using a PET scan. I know there's always research into new isotopes for better imaging, as well as cancer treatments. There's always cancer treatment research for like charged particle beams to precisely destroy tumors and such. Um, as for outside of the medical field, there's a little bit of research going into like neutron imaging systems. They work sort of like X-rays, but instead of using X-rays, we use neutrons, and neutrons are going to get stopped by different materials. So we're going to be able to see through different materials and get a sort of a different image from maybe materials that an X-ray couldn't see through.
Yeah. Um, and then I was about to ask about national labs. I guess that's classified, maybe like weapons research and that kind of stuff. But uh,
Yeah. So actually, I don't know a whole lot about national labs. I haven't worked at a national lab, so I'm not too familiar with the type of research that goes on there. But national labs, it doesn't always mean weapons research. A lot of the national labs that we have don't do weapons research. They do more material or other research projects, physics based. There are some weapons research being done, probably mostly done at Y12, the U.S. facility for nuclear weapons. Um, but again, I don't know anything about that.
yeah,
So
yeah. Um, so with your nuclear science undergraduate degree, so you said you kind of split off into power and then you split off in medical. So if you do take that track, would it be easy to switch to another one if you still wanted to?
yeah, so up until you really get into either the energy or the medical focused classes in your senior year, you can pretty freely switch between the two. It's not something that you actually have to declare. It's something that you talk through with your course advisor and your faculty advisor, which one you really want to follow through. I know the majority of students that come through the Madison degree go into the energy track. However, there are a few that do choose the health physics track. Um, and that really just probably focuses more on courses in um, actually I don't even know. I haven't looked into that track a whole lot, but both tracks do require like an ionizing radiation course where you learn about ionizing radiation and how it affects the body and like tissue and such like that, so that we're able to maintain a good standard of safety around radiation.
Yeah.
But as for the ease of switching between, I believe it is pretty easy to switch. Until you get past your senior year. By that point, you're already graduating. So if you want to go back and get another degree, I'm sure you could go and do that too.
Yeah. To end off with, I wanted to ask what advice you'd have for someone who's still in high school who wants to go into nuclear engineering.
Yeah, still in high school. Just general advice in high school: enjoy high school. High school is a good time. Um, However, if you're looking to get into nuclear engineering, definitely reach out to a university that has a nuclear engineering program. I know our head of the department, Wilson here, loves getting in touch with high school students that are interested in nuclear engineering, engineering physics, anything like that. And I know a lot of other universities are as well. They want to grow their nuclear program. So definitely get in touch with a university and go tour it, see if you enjoy it. Talk to some of the students there. All the students, well, I shouldn't say all. I'm sure quite a few of the students would enjoy talking with you about their major, about what they do there, and definitely enjoy your math and physics courses, because there's a lot of math and physics in nuclear engineering.
Yeah. All right then. Thank you for meeting with me.
Yeah, no problem. Thank you for having me.